Hello everyone, welcome to the OneClass channel. My name is Marlyn. I'm a second year chemical physics student at the University of Waterloo with a minor in math. Today I'm going to be going through some high school level and college level calculus problems. Be sure to check out the links in the description if you're in need of any extra homework help or like some one-on-one tutoring. Okay, let's get into it. So for our first question, we'd like to evaluate cos 4 pi over 3. And there are a couple ways to do this question. So I'm just gonna walk you through all of them. Okay. So we have cos 4 pi over 3. And so method 1. Would be the unit circle. So we're just going to go ahead and draw that out. Okay, and that's going to be our unit circle. And then now let's plot our points. And so we have pi over 2. Sorry, let's start 0. Pi over 6. Pi over 4. Pi over 3. 2 pi over 3, 3 pi over 4, 5 pi over 6, pi, 7 pi over 6, 5 pi over 4, 4 pi over 3, 3 pi over 2, 5 pi over 3, 7 pi over 4, and 11 pi over 6. Okay, and so just in case you don't know how to, or you haven't seen radians, just so you know, pi is 180 degrees. So for example, when I say pi over 3 in degrees, that would be 180 degrees over 3. And that is going to give me 60 degrees, just as an example. Okay, now how the unit circle works is my x-coordinate is going to be, my x-coordinate so I have xy, and there's going to be cos theta, sine theta. Okay, so this is pi over 2. So starting at 0, cos 0 is going to give me 1, sine 0 is 0. Cos pi over 6 is root 3 over 2. Sine pi over 6 is 1 over 2. Let me put this somewhere else. Okay, and then we come to pi over 4, which is going to give me root 2 over 2, root 2 over 2. And if you just keep on putting in these angles into cos theta and sine theta, you should be able to plot the entire circle. So I'm just going to fill it in really, really quickly for you. Pi over 2 is going to give me 0, 1. 2 pi over 3 is negative 1 over 2, root 3 over 2. 3 pi over 4 is negative root 2 over 2, root 2 over 2. 5 pi over 6 is negative root 3 over 2, 1 over 2. Pi is negative 1, 0. 7 pi over 6 is negative root 3 over 2, negative 1 over 2. 5 pi over 4 is negative root 2 over 2, negative root, sorry about that. So negative square root 2 over 2, negative square root 2 over 2. 4 pi over 3 is going to give me negative 1 over 2, negative square root 3 over 2. 3 pi over 2 is going to give me 0 minus 1. 5 pi over 3 is 1 over 2, negative root 3 over 2. 7 pi over 4 is root 2 over 2, negative square root 2 over 2. And lastly, 11 pi over 6 is root 3 over 2, negative 1 over 2. Okay, and so I'm just going to look for 4 pi over 3. I see that I have it here. Remember that x is my cos theta, y is my sine theta, and so I will have, just by looking at the circle, that cos 4 pi over 3 is equal to negative 1 over 2. And so you can notice that there's a bit of a pattern here. 1, 0, root 3 over 2, root 2 over 2, 1 over 2, 0. And if you just keep reading the x coordinate, I make all of these negative and go back down until I hit negative 1, 0. So same way that I said root 3 over 2, sorry, the same way that the closest one to here is 1 over 2, I make that negative, so negative 1 over 2. Then negative square root 2 over 2, it matches its opposite, negative square root 3 over 2, negative 1, 0. That's how you read the top half. The bottom half is similar. You'll notice root 3 over 2, negative root 3 over 2, root 2 over 2, negative root 2 over 2, 1 over 2, negative 1 over 2. And so it's best to try and recognize these types of patterns, and it's going to make it a lot easier for you to remember how to draw it up, because it's really easy to read your angle answers off of it. Now for our second method, we'll be using the fact that where is it? So cos pi minus theta is equal to negative cos theta. Just one moment. Sorry. Plus theta. Yeah, negative cos theta. There we go. And so that's just a supplement angle identity. And this also reads off of the unit circle. So as I said, if I add pi to 0, for example, and come all the way here, I'm going to get the negative answer, so negative 1. The same thing, if I add pi to pi over 6, I get 5 pi over 6. Sorry, I get, yeah, if I add pi to pi over 6, I'm going to get 5 pi, sorry, all the way to the opposite side, so 7 pi over 6, and I'm going to get negative square root 3 over 2. And so it's just reading the opposite line is going to give me the negative value in the cos position. You also have another identity, which is cos pi minus theta is equal to negative cos theta, and that is read similarly here. Pi minus pi over 6 is 5 pi over 6. When I come here, root 3 over 2, negative root 3 over 2. So it's just reading these patterns off of that same unit circle and driving these general formulas that one can easily memorize and spit out what the answer is. And so I have cos pi plus pi over 3 is equal to negative cos pi over 3. Now the reason why I wanted this pi over 3 is because I know how to find it very, very easily using the special triangles. So if I just draw these out, I get pi over 6, pi over 3, 1 over 2, h, root 3 over 2, h. And so using SOHCAHTOA here, I will have that cos pi over 3 is equal to adjacent over hypotenuse, so 1 over 2 h over h, and that's 1 over 2. So cos 4 pi over 3 is going to be negative 1 over 2. So just to remind you, recognizing these patterns helps you generate these general formulas where you can strictly use the special triangles to get your answer for what would be in this position, and then you just take whether it's the negative, the positive, by 2, by 3, whatever it's telling you to do, you just do it to the answer, and that's it. So if you know your special triangles, you'd be fine. If you know how to draw out the unit circle, you'd also be fine. And that's going to be it. Okay, next up, we have an integration. And we would like to integrate cosecant cubed from pi over 6 to pi over 3 cosecant cubed x dx. And so for this one, we're going to be using integration by parts. So let's just write down that formula very, very quickly. The integral of u dv is equal to uv minus the integral of v du. So now we need to make our choices for u and dv based off of what we have here, so that we can figure out what our du and v are going to be and write out our formula. And so we can choose what our u and dv are going to be according to this little acronym here, which is ILATE, and that is inverse trig, logarithms, algebraic expressions, trig expressions, and exponential. Okay, and so I can see that I bump into inverse trig first, which means I'm going to set my u equal to cosecant theta, which means that my, so let's write that down, which means that dv must be equal to cosecant squared theta. And so my v is negative cotangent theta. Let's go about finding our du. Du over d theta is equal to d over d theta of 1 over sine theta. And then I'm going to apply my quotient rule. And that just states that d over dx of f of x over g of x is equal to the derivative of f by g of x minus the derivative of g by f of x all over g of x squared. And so that means that in our case we have f of theta is equal to 1, so the derivative of that is equal to 0. And we have g of theta is equal to sine theta, and so the derivative of that is cos theta. And so when you put that all together, we get 0 by sine theta minus 1 by cos theta all over sine squared theta. We can now forget about all of this and just simplify that. And so we get negative cos theta over sine theta by 1 over sine theta, and this is negative cotangent theta cosecant theta is equal to du over d theta. So du is equal to negative cotangent theta cosecant theta d theta. And so let's just write that in over here. du is negative cotangent theta cosecant theta d theta. Okay, so now we can get back to doing our integral now that we have all of its pieces. Okay, so using this formula that we have here, we get that the integral from pi over 6 to pi over 3 is equal to uv, so cosecant theta multiplied by negative cotangent theta minus the integral of negative cotangent theta multiplied by negative cotangent theta cosecant theta d theta. Okay, so we're going to have to solve this too. So let's go about doing that. And from here we get negative cosecant theta, cotangent theta. Negative is going to leave a positive on the inside, and so we're going to remain with a minus here. The integral of cotangent theta squared, cosecant theta d theta. Okay, now from there we are going to use an identity. And that identity is going to be the fact that cotangent squared theta is equal to cosecant squared theta minus 1. I'm just going to put that right back in here so that we can get that the integral, that what we're looking for is negative cosecant theta cotangent theta minus the integral of cosecant squared theta minus 1 into cosecant theta d theta, and this is equal to the integral of cosecant cubed theta d theta. And so this is going to give me negative cosecant theta cotangent theta minus the integral of cosecant cubed theta minus cosecant theta d theta. Okay, and then I'm going to use another property here, and that is the fact that I can split integrals up. So let me just write that out. The integral of f of x plus g of x all over d of x is the same thing as if I integrated them separately. That's the integral of g of x dx. So I'm going to just apply that here to split this up. And I will get that the integral of cosecant cubed theta d theta is equal to negative cosecant theta cotangent theta minus the integral of cosecant cubed. So let's just put this all in brackets. Theta d theta minus the integral of cosecant theta d theta. So I noticed something familiar here, and I'm going to choose to move it to the other side. That way I have all of the cosecant cubes on one side and everything else on the other side. And so from this I get that 2 by the integral of cosecant cubed theta d theta is equal to negative cosecant theta cotangent theta plus, because minus by minus, the integral of cosecant theta d theta. And this we had, just one moment. Okay, and so we get this. And so now we have to go about finding this integral. And so how we're going to go about finding that is we'll have to do it on the side. And so if we multiply everything by cosecant theta plus cotangent theta over cosecant theta plus cotangent theta, and then you're going to multiply this all by cosecant theta in an attempt to simplify this into a form that we can integrate. And so this is 1 technically, so we're allowed to do that. And so we'll get the integral of cosecant squared theta plus cosecant theta cotangent theta all over cosecant theta plus cotangent theta d theta. And then we're going to make a substitution here. If we choose u as cosecant theta plus cotangent theta, we get du is equal to du over d theta would be equal to negative cosecant squared theta minus cotangent theta cosecant theta. And so that means that d theta is equal to du over negative cosecant squared theta minus cotangent theta cosecant theta. And so we're going to substitute this all back in to what we have up here. And we get that the integral of cosecant squared theta plus cosecant theta cotangent theta over u, and you put in your d theta, so du over -1 into cosecant squared theta plus cotangent theta cosecant theta. So you see that these two will cancel, and we get negative the integral of du over u, which is going to be negative ln the magnitude of u. And then we just put back in what our u is. So this will be negative ln the magnitude of cosecant theta plus cotangent theta. And so this is not our final answer, it's what is going to end up here. And so we get that the integral, so 2 by the integral of cosecant cubed theta is equal to negative cotangent theta cosecant theta plus negative ln the magnitude of cosecant theta plus cotangent theta. Okay. And then we're just going to solve for what we're looking for. So we get the integral of cosecant cubed theta d theta is equal to negative cotangent theta cosecant theta minus ln the integral of cosecant theta plus cotangent theta all over 2. Okay, and then we need to remember the fact that we are integrating from pi over 6 to pi over 3. From pi over 6 to pi over 3. Okay, and so now we need to go about finding that. So we have negative cotangent pi over 3 cosecant pi over 3 minus ln the magnitude of cosecant pi over 3 plus cotangent pi over 3 all over 2 minus the same thing but with pi over 6. And so we have so cotangent pi over 6 plus cosecant pi over 6 magnitude over 2. And so when you put that all into your calculator, you should get a final answer here. Let's just zoom out so you can see everything a little bit better. Okay, and so you'll get a final answer of 1.78254. And so depending on the number of significant figures that you've been asked for, you'll cut it off where it needs to be cut off. And that's going to be it for this question. Okay, next up, we are going to be looking for the derivative of secant x multiplied by tan x. So we're going to be making use of some rules here. Okay, so we'll be making use of the product rule, which just states that d over dx of f of x by g of x is equal to df over dx by g of x plus dg over dx by f of x. Okay, and so we have that our f of x is equal to secant x, which is 1 over cos x, and our g of x is equal to tan x, and that is sine x over cos x. Okay, so now I need to go about finding the derivatives of these, and I'm going to do that by using another rule, which is a quotient rule, and that just states that d over dx of, we're going to have to name them different functions, so m of x over n of x is going to be equal to the derivative of m multiplied by n minus the derivative of n multiplied by m all over n of x squared. So now let's go about finding these. I have that so I'm going to have to split it into two cases. For f of x, I have that my m of x is equal to 1, so its derivative will of course be 0. And for my n of x, it is equal to cos of x, so its derivative is equal to negative sine of x. And so the derivative df over dx will be 0 multiplied by cos x minus negative sine x multiplied by 1 all over cos x squared. So this will give me 0, and these two will cancel to yield a positive, and so I will get sine x over cos x by 1 over cos x. And so the derivative of secant x is equal to tan x secant x. Now next up, I'll have my tan of x. Let's just make sure everything here makes sense. So now I do my second case of g of x. So in this case, m of x is equal to sine x. Its derivative will therefore be cos x. N of x is equal to cos x, and its derivative will therefore be negative sine x. And so when I put that all back into my formula here, I will get cos x by cos x minus sine x by negative sine x. And this will all be over cos squared x. This will give me, these two negatives will cancel to yield a positive. So cos squared x plus sine squared x all over cos squared x. We need to note the identity that cos squared x plus sine squared x. Let's just write that out. Cos squared x plus sine squared x is equal to 1. And so I can swap this all out for 1. And I will get 1 over cos squared x, and that is equal to secant squared x. And so that's going to be my derivative of g of x is secant squared x. Okay, so now that I have those, I can put them back into my product rule and find my final answer. Just one moment. Okay, so back up here, I put this all back into this formula, and I get that the derivative of secant x tan x is equal to df over dx, so tan x secant x, multiplied by g of x, so tan x, plus dg over dx, so secant squared x, multiplied by f of x, so secant x. Okay, and then multiply out. So I get tan squared x secant x plus secant cubed x. And that's going to be my final answer. Oh, correction. So let's factor out a secant x. And I get tan squared x plus secant squared x. And then I just need to note that secant squared x is equal to 1 plus tan squared x, which is an identity, to just help simplify this a little bit more. And so I get, when I put that in, I will get secant x into tan squared x, and then put in your secant squared x, so plus 1 plus tan squared x. And this will give me secant x into 1 plus 2 tan squared x. And that's going to be it. Okay, next up, I'm going to be evaluating the integral of ln of x over x. And so again, I'll be using the integration by parts. So the integral of u dv is equal to uv minus the integral of v du. Again, use ILATE to choose your u. So inverse trig, logarithmic, algebraic, trig, and exponential. Okay, and so I bump into logarithmic first because I have ln x, and that is what I'm going to choose as my u. That means that dv is equal to 1 over x. This means that v is equal to ln x, and du is equal to dx over x. Okay, so now that I have all of that, I'm just going to plug everything back into my formula, and I get that the integral of ln x over x dx is equal to, sorry, this is dx, is equal to, so uv, so ln squared x, minus the integral of ln x by du over x dx. And so I'm just going to move everything that's common to one side, and I get 2 by the integral of ln x over x dx is equal to ln squared x. And so now I'm just going to isolate. So ln x over x dx is equal to ln squared x over 2. And then I need to remember that this is an unbounded integral, and so there will be a plus c. And that's going to be the final answer for this question. Okay, on to our next question. Okay, so for this one, I would like to find a non-zero vector that is orthogonal to the plane through the points, these ones, and find the area of my triangle. Okay, so first I need to find two vectors on the plane based off of the points I've been given. Let's go about doing that. So A would be to find two vectors on plane. Part B is going to be to cross the two vectors I've just found in order to find my perpendicular vector. And then for part C, I'll be using that perpendicular vector in order to determine the area of PQR. Okay, so for my two vectors, I will choose PQ, and that is going to be point Q minus point P. So -2 minus 1, 1 minus 0, 3 minus 1. And this is going to give me -3, 1, 2. Next up, I have PR. So I chose P in both cases so that these vectors aren't parallel to one another. So you have the first one staying the same, and then you change these last two letters since I have 3 points. And so this one will be R minus P, and that is going to be 4 minus 1, 2 minus 0, and 5 minus 1. And that will give me 3, 2, and 4. So these are my two vectors. Next up, I'm going to want to cross them in order to determine my, I'll call this R1 and R2, in order to determine my perpendicular vector. So R1 cross R2 is going to be I, J, K. And then I put in my first one, so a -3, 1, 2. And then my second one, 3, 2, 4. And I go about crossing them. And so I will get that in my I component, I will have 1 by 4 minus 2 by 2 minus my j component, which will be -3 by 4 minus 3 by 2, plus my k component, and that one will be -3 by 2 minus 3 by 1. Okay, and so I'm just gonna write that down as a vector. So I will get n is equal to 4 minus 4, so 0. For j, I will have -12 minus 6, so -18, but it's by -1, so that's just going to be 18. And then in my k component, I'll have -6 minus 3. Okay. So now I have my perpendicular vector. And please note that if we look at a surface, I can have the perpendicular vector pointing outwards towards me or inwards. So I can also reverse this and have the second perpendicular vector that's pointing in the opposite direction, which would be that. Okay, so now I'm going to use this to find the area of the triangle, and the area would be 1/2 the square root of what's in my x component plus what's in my y component plus what's in my z component, but this is all of my normal vector. So this is going to be 1/2 by 0 squared plus 18 squared plus -9 squared. No matter which vector you chose, you'll get the same answer because a negative number squared is just that number squared. So this will give you 1/2 the square root of 324 plus 81. And that is 1/2 the square root of 405. We're going to use some square root properties in order to simplify this. The square root of a by b is equal to the square root of a multiplied by the square root of b. So what I'm going to do is I'm going to write this as a product of two numbers, and I'm going to choose them wisely such that one of them is a perfect square. And so if I choose 5 by 81, will give me a half. By the square root of 81 is going to be 9 square root 5. So this is 9 over 2 by the square root of 5. And if you put that into your calculator, that's going to give you 10.0623. And that's it for this question. Okay, next up, I have another integration. And I'm looking for the integral of 1 over 2x dx. So let's just need some integral properties. I know that the integral of a constant by some function of x dx is equal to the same thing as if I just pulled out that constant and did the integration of the function itself. And so here I can see that 1 over 2x is equal to 1 over 2 multiplied by 1 over x. And so this is going to be my constant, and I'm just going to pull it right out so that I can get that the integral of 1 over 2x dx is equal to 1 over 2 by the integral of 1 over x dx. I know this integral, it's a common integral, and it's going to give me ln the magnitude of x plus c. And so my final answer will be ln the magnitude of x over 2 because of that constant I pulled out, plus c. Okay, next up, I'm looking for the derivative of ln x over ln y. So, you could do this in two ways. And that's just by noting that ln x over ln y is equal to ln x minus y. Okay, so, I know that d over dx of f of x over g of x, just one moment, Okay, sorry about that. So back to the quotient rule. So the derivative of f of x over g of x will be df over dx by g of x plus dg over dx by f of x. Okay, so in the case of ln x over ln y, I will have f of x is equal to ln of x. The derivative of this is going to be equal to 1 over x. And then, sorry, just one moment, g of x is equal to ln of y. Now this is going to be not 1 over y, and that's because if y is a function of x, then I'm going to have to take the derivative of that. And so the derivative of g of x will be 1 over y by the derivative of y, so dy over dx. And so we're just going to put that all back into our, oops, my apologies, I wrote the wrong formula here. This is supposed to be the derivative of x by g of x minus the derivative of g by f of x over g of x squared. So the formula I wrote before is the product rule, which the quotient rule is actually derived off of. But yeah, and so when I put that all back in, I get that d over dx of f of x over g of x is going to be equal to, so the derivative of x, sorry, f of x, so 1 over x multiplied by g of x, so ln y minus the derivative of g of x, so 1 over y multiplied by dy over dx. That is multiplied by f of x, so ln x, all over g of x squared, so ln y squared. Okay, and then I'm going to simplify this. Sorry, just one moment. So I get ln y over x minus ln x over y multiplied by dy over dx, all over ln of y squared. And we can rewrite this as ln of y squared over x minus y minus dy over dx by ln of y squared over x minus y. And that's going to be your final answer. So you can leave it in either forms, both are correct. Okay, next up, I'm looking for the derivative of cos xy. And so let me just write down the rule that I talked about in the last question. And that is, if I have f of g of x and I'd like to find its derivative, I'm going to take the derivative of f as a function of g of x over dx, and then I'm going to multiply that by dg over dx. And so just as a quick example, if I had x squared plus 2 all to the power of 1 over 2, my f of x is equal to my f of g of x is equal to g of x to the power of 1 over 2, and my g of x is equal to x squared plus 2. So df over dx is going to be 1 over 2 g of x to the power of negative 1 over 2 multiplied by dg over dx, and that's going to give me 2x. And so when I put that all together and I put back in what g of x is, which is x squared plus 2, I will get 2x over 2 x squared plus 2 to the power of negative 1 over 2. These 2's will cancel, and I will get x over the square root of x squared plus 2. So that's just how you utilize the rule I've just written down for you. Now let's apply it to what we have here. This is the chain rule, I believe. Okay, so I have cos of u, basically. I'm looking for d over dx of cos of u. Okay, and this is going to be equal to d cos u over du multiplied by, it's supposed to be dg, multiplied by du over dx. Okay, and so the derivative of cos u with respect to u is going to give me negative sine u. And as I said, my u is equal to xy, so its derivative is equal to y. And so this is going to give me multiplied by, if y is a function of x, which we are not told here, then du over dx is going to utilize the product rule, and it is going to be the derivative with respect to x first, which is y, plus x dy over dx. Okay, so now I'm just going to put that all into there, and we get that d over dx of cos xy is going to be equal to negative sine u multiplied by y plus x dy over dx. And this is just going to give us negative sine. You put back in your u, so xy multiplied by y plus x dy over dx. And that's going to be it for this question. Okay, next up I'm looking for the derivative of secant squared x. Okay, so again, I'm going to choose to use the chain rule. So dy over dx is equal to dy over du by du over dx. Okay, so my u will be secant x, and my y is u squared. Okay, so dy over du is going to be 2u. That's easy to see. Now we need to find the derivative of secant x. So d over dx secant x, and I just need to note that secant x is 1 over cos x. Okay, and for this, again, I'm going to use the quotient rule. And that just leaves the d over dx of f of x over g of x is the derivative of f by g of x minus the derivative of g by f of x all over g of x squared. So now when I put in what I actually have, I have f of x is equal to 1, so its derivative is equal to 0. And then g of x is equal to cos x, and so its derivative is equal to negative sine x. And so that is going to mean that d over dx of 1 over cos x is going to give me 0 by cos x minus 1 by negative sine x all over cos squared x. These two negatives will cancel. This gives me a 0. And so all in all, I get that du over dx is equal to sine x over cos x by 1 over cos x. And that will give me tan of x by secant x. Okay, and then that's just what I'm going to put back in up here. So du is tan x secant x du over dx. Okay, so now I can erase what I wrote down on the side before to find my du over dx. Okay, and so finally I get that d over dx of secant squared x is going to be dy over du, so u squared, and I'm just going to put back in the fact that u is secant x. So secant squared x by du over dx. So tan x, secant x. This is going to give me secant cubed x by tan x. Okay, and then, sorry, dy over du, my apologies. This is supposed to be 2u. So 2 secant x. So be careful with what you're putting back in. So this is going to be 2 secant squared x by tan x, and that's going to be your final answer. Okay, next up, I'd like to determine whether the series is convergent or divergent, and I can do that by just taking the limit as n approaches infinity. So what I'm basically asking myself is, as n approaches this infinity that I'm trying to sum it to, what is what I'm summing going to start behaving like? Is it getting bigger? Is it getting smaller? If it's approaching 0, then after a certain point I don't need to continue adding zeros because that doesn't do anything, and that would make it convergent. But if it doesn't approach 0 and it's approaching infinity instead, so it's growing, that means that I can't cut off those values and it's going to be divergent. I can't convert this summation into a simple mathematical expression like 1 over x or a number, for example. So let's find the limit as n goes to infinity. And so my limit of 1 over 9 plus e to the negative n. Okay, so as n goes to infinity, e to the minus n starts approaching 0, right? And so this means that the limit as n approaches infinity is going to be 1 over 9 plus 0, and that's just going to be 1 over 9, which is not going to be 0. So I don't reach a point where I can just cut off terms and give you a specific number. I will have to continue summing until infinity. And so that is going to mean that this series is divergent. I can't simplify it. Okay, next up we have a differential equation. And so I have that dy over dx is equal to negative 2x over y. And so I'm just going to bring all of my like terms to one side, and I get y dy is equal to negative 2x dx. And then I'm going to integrate both sides. The integral of y is going to be, 1 over 2y squared. Let me just write that down. So the integral of x to the power of a over dx is 1 over a plus 1 x to the power of a plus 1. And so in the case where my a is 1, it's going to become 1 over 2 y to the power of 2. So y squared over 2 is equal to, I'm going to pull out the negative 2, and the integral of x dx is what is going to be left over. And that comes from the fact that a constant multiplied by f of x, and you integrate that, is the same thing as if I just pulled out the constant and integrated f of x. And so, similarly to how I applied this, I have x dx, and so I'll get negative 2 over 2x squared. These two will cancel, and I'll get y squared over 2 is equal to negative x squared plus c. I'm going to put the plus c on the other side because I'm looking for y as a function of x. So the plus c is best on that side. Okay, and then I'm going to move over the 2, and this will give me y squared is equal to negative 2x squared plus c. And then I'm going to solve for y, so this is going to be the square root. So y is equal to 2 by negative x squared plus c, the square root of all of that. Okay, now I've been given a specific solution, and I have f of 1 is equal to -1. And so I can figure out my plus c from this. I have -1 is equal to the root of 2 into -1 squared, which is -1 plus c is equal to -1. So -1 squared is equal to 2 by -1 plus c. -1 squared is 1 is equal to 2 by -1 plus c. And so I will get 1 is equal to -2 plus c. Move this over and I will get 3 is equal to c. And so I'm going to put that back into my general formula, and I'll get that y is equal to the square root of 2 by -x squared plus 3. Okay, and that's going to be it for this one. Oh, oh, this is 2c. So be careful with your factors. This is going to be 2c when you multiply it in. So when I move this over, this will form 3 is equal to 2c, divide out the 2, and I get c is equal to 3 over 2. And so I get that the general formula becomes y is equal to the square root of 2 by -x squared plus 3 over 2. And that's going to be it for this question. Okay, next up we're looking for extrema, and we have that f of x is equal to x plus 16 over x. I'm trying to find extrema in the range 4, 25. So from x is equal to 4 to x is equal to 25. Okay, so what we're going to do is we know that the derivative, so df over dx, is equal to, if I have a function like that, for example, df over dx at a specific point is going to be the slope of the tangent line at that point. And so obviously I can see that at extrema, the slope of the tangent line is 0. So if I look for points where the derivative of the function, so the slope of the tangent line, is 0, I can find my extrema. So let's go about doing that. So I would like to look for df over dx, which is equal to d over dx of x plus 16 over x. Okay, now I'm going to apply the general rule that d over dx of g of x plus m of x is going to be equal to d over dx of g of x plus d over dx of m of x. And so I'm just going to apply that to split this up. And I will get the df over dx is going to be d over dx of x plus d over dx of 16 over x. So this one is quite simple. I'm going to apply the exponent rule, and that just states that d over dx of x to the power of a is 1 over a minus 1 x to the power of a minus 1. Sorry, a x to the power of a is equal to a x a minus 1. Okay, so I have the power of 1 here, and so I'll get 1 x to the power of 0, which is just 1. And so I'm going to get 1 plus d over dx 16 over x. Okay, now I want to deal with this derivative. And I'm going to use another rule, and that's just that the derivative of a constant by some function of x is the same thing as if I just pulled out that constant and taken the derivative of that function of x. And so I'm going to pull out that 16. So So I can get df over dx is equal to 1 plus 16 d over dx. And then I'm going to write 1 over x as x to the power of negative 1. So x to the power of negative 1. Okay, next up I'm going to apply the same exponent rule to deal with that. And it's going to give me 1 plus 16 by negative 1 x to the power of negative 2, according to this rule. And so finally, that will give me that df over dx is equal to 1 minus 16 over x squared. Okay, and remember I want to set it equal to 0 and find my x values at that point. So I'll get 1 is equal to 16 over x squared. Bring the x squared over, and I get x squared is equal to 16. And so I will get x is equal to the positive or negative square root of 16. That means x is equal to positive or negative 4. But I need to be careful. I've been told I only want the maximum and minimum values in the indicated interval, which is from 4 to 25. So this minus 4 isn't within there, so I'm just going to cancel it, and I will have my my extrema at x is equal to 4. Okay, now let's find what f of x is at that value. And so I have f of x is equal to 4 plus 16 over 4, and that is going to give me 4 plus 4, which is 8. Now I want to analyze the behavior of the function before and after this point that I've just found. So again, return to that mental image of your function. So at extrema, we said that the slope is equal to 0. Now you'll notice that when the function is decreasing, such as here, the slope is less than 0, and when the function is increasing, the slope is greater than 0. That means, therefore, that if I go from a slope less than 0 to a slope that's greater than 0, so if I analyze the derivative of the function before and after my point, which is x is equal to 4, and if I get a negative before and a positive after, that means I have a minima because it was decreasing and then it's increasing. If I go from the slope is positive to the slope is negative, that means I was increasing and then decreasing and I have a maximum. So let's go about figuring out whether it's a maximum or a minimum. Okay, so I know that the derivative of my function is 1 minus 16 over x squared, right? So now let's examine some points before. E.g. at x is equal to 2, then the derivative of the function is 1 minus 16 over 2 squared, which is 4. That is going to give me 1 minus 4, and that's negative 3. So it's negative before I hit my extrema. Let's check after. E.g. at x is equal to 5. I get that this is equal to 1 minus 16 over 5 squared, so that's going to be 25. 16 over 25 is 4 over 5. Sorry, 0.64. And that is, of course, going to give me 0.36, which is positive. So I'm going from a slope that's decreasing to a slope that's increasing, which tells me that this 8 value is going to be, that at x is equal to 4, I have a minimum. And it is going to be an absolute minimum within the interval that they've given us because I haven't found any other extrema values. And so my final answer is that I have an absolute minimum at x is equal to 4, and we said that f of x is going to be equal to 8 at that point. Okay. Okay, next up, I'd like to evaluate the indefinite integral as an infinite series. So I'm looking for the integral of arctan x squared. So first, how I'm going to deal with this is I'll find the infinite series for arctan x, which will lead me to finding the infinite series for arctan x squared by substitution. And then for my second part, I will integrate that. Okay, so first off, I need to remember the fact that arctan x is going to be the integral of 1 over 1 plus x squared dx. Okay, I know that from my common integrals. And so I can make an observation here. If the infinite series for 1 over 1 minus x is equal to the summation of x to the power of n from n is equal to 0 to infinity, what that means is that when I have 1 over 1 minus x squared, I can just substitute that in, and I will get the summation from n is equal to 0 to infinity of negative x squared to the power of n. I'm going to simplify that. We're going to distribute out the minus as a minus 1 to the power of n. So n is equal to 0 to infinity, negative 1 to the power of n, x to the power of 2n. So this is going to give me this. And so that means that arctan x is equal to the integral of this summation. N is equal to 0 to infinity of negative 1 n x to the power of 2n all over dx. And so I'm only going to be dealing with variables that involve x. And so the summation, of course, doesn't, and the minus 1 does not. So I will not touch them. I'm going to deal with this x to the power of 2n. And I need to just remember the general rule that the integral of x to the power of a over dx is 1 over a plus 1 x to the power of a plus 1. And so in my scenario where a is equal to 2n, I'll get 1 over 2n plus 1 x to the power of 2n plus 1 in the place of x. And so when I put that all back in, I'll get the summation, because as I said, we are not touching these two, they don't involve x, negative 1 to the power of n, x to the power of 2n plus 1, all over 2n plus 1. Okay, so now I have arctan x, and I need to go about finding arctan x squared. So what I'm going to do is, again, I'm just going to substitute x squared into here, and I'll get that it is the summation from n is equal to 0 to infinity of negative 1 to the power of n. I put x squared in the place of x to the power of 2n plus 1, because x was to the power of 2n plus 1, all over 2n plus 1. Next up, I use a property of exponents, and that is just x to the power of a to the power of b is x to the power of a by b. And so in the scenario of 2 and 2n plus 1, I have x to the power of 2 to the power of 2n plus 1 is equal to x to the power of 4n plus 2. And so I get that it is this summation instead. X to the power of 4n plus 2 all over 2n plus 1. And that is my arctan x squared. But this is not where the question ends. They're asking me to integrate arctan x squared. So let's go about doing that. It's going to be in a similar fashion to how we integrated this. And so I'll get that the integral of arctan x squared is equal to the integral of this infinite series. So negative 1 to the power of n, x to the power of 4n plus 2, all over 2n plus 1. And I'm going to treat it in a similar fashion -1 to the power of n, 2n plus 1, and my summing symbol don't involve x in any way. So I'm going to focus in on the x and deal with that. And so again, recall the integral of x to the power of a over dx is 1 over a plus 1 x to the power of a plus 1. And so in the case of 4n plus 2, the integral of x to the power of 4n plus 2 over dx is going to give me 1 over 4n plus 3 x to the power of 4n plus 3. And so that's what I'm going to put in. And I will get that it is going to be the summation from n is equal to 0 to infinity of -1 to the power of n x to the power of 4n plus 3 all over 2n plus 1 into the 4n plus 3. And that's going to be it for this question. Oh, and don't forget about the plus c. I have an unbounded integral. Okay, now we're going to be dealing with how to find the maximum value of a function. There are many ways to do this, all not of equal use, of course. So method 1 would be to simply graph the function. If you're given the function, just plot a bunch of points, and within them, when you plot your x to y, so let's say I'm plotting some function, and I have x and I have y. I get 0, 1, 2, 3, 4 as an example. And at 0, y is 0. At 1, it's 2, 4, and then it starts decreasing. And so, of course, I'm going to notice that 4 is this maximum value because I see that y is increasing and then decreasing. So I have my maximum. But if I have a very complex function that is in small increments, for example, this is going to be basically a waste of my time. It's going to take way too long. There's other more sophisticated methods that I could use. And so let's go about finding those. So as I discussed earlier, we can use derivatives, and we can just notice that, for example, for this function, at this turning point, so at this extrema, my slope is equal to 0. Before the extrema, so in the case of the extrema being a minima, my slope goes from less than 0, so negative, to positive. A good way to remember what slope is positive, a tick is good for you. The slope of a tick is positive. Okay, so now in the case where I'm looking for a maximum, what I'm going to be looking for, let's just draw that out, is I'm looking for the slope going from over 0 to 0 to less than 0. Okay, so let's see. Let's say we have the function, just as an example, f of x is equal to, 2 into x squared plus 1 minus 3 as an example. Okay, so as I said earlier, we're going to look for the derivative. And so if I expand this out, I have f of x is equal to 2x squared plus 2 minus 3, which is 2x squared minus 1. Okay, so now I find the derivative of that, and I'll get 4x, and I'll set it equal to 0. Okay, so obviously it will be at the point x is equal to 0. Let me just ensure everything is correct with that. Yep. Okay, and so it's going to be at the point x is equal to 0 is when the slope is going to be 0. Now I need to determine whether this is going to be a maximum or a minimum, and I'm going to use these two. And so I'm going to examine some points before my extrema and after my extrema. So let's try f of minus 1. which will be 2 minus 1 squared plus 1 minus 3. Okay, and then I will get 2, 1 plus 1 minus 3, which is 4 minus 3, which is 1. So before, I have my slope is greater than 0. Okay, now let's check after. I'll get 2 into 1 squared plus 1 minus 3. And so from this, again, I will get 2 by 2 minus 3, which is 4 minus 3. Sorry, just one moment. I don't think I got a good example. Just go back to my function. It is 2x squared minus 1. Sorry. It should be 2 minus 1 squared minus 1, which is 2 minus 1, giving me 1. Okay, next up, f of 1. Sorry, this was not the best example to use, so I'm just going to change it. Just so I can get one with both minima and maxima, so we can clearly see the difference. Oh. Okay. So as an example, let's take 2x minus 1 cubed plus 5. This is going to be our f of x, and let's analyze this graph without plotting the points at all. So just using the derivatives, and we get that the derivative of this is going to be, I'm going to use the product rule. Let me just rewrite that. Okay, so now I need to find df over dx, which will be df over du by du over dx, and I'll set u as equal to x minus 1. So df over du is going to be 3u squared multiplied by 2, so 6u squared, and then du over dx is by 1. And so this will give me 6x minus 1 squared by 1, and that's going to be my derivative. Okay. So next up, I want to set this derivative equal to 0. So that is 6x minus 1 squared. And this will, of course, be 0 when x minus 1 is equal to 0. So x is equal to 1. Sorry, I'm trying to find the best example to showcase what it is that I'm trying to showcase. Okay, let's pull one from the question here. And let's look for the maximum of negative x squared plus 3x minus 10. Okay? Okay, so the derivative of the function will be negative 2x plus 3. We're going to set that equal to 0 as I discussed earlier. I'm going to move the 2x over, so I get 2x is equal to 3, and so it will be at x is equal to 3 over 2. Okay, now let's examine points before and after that on my f of x. Sorry, on my derivative. So f prime of, let's try, so this is equal to 1.5. So let's try the point 1 over 2. And I'll get negative 2 by 1 over 2 plus 3. And this will give me negative 1 plus 3, and that will give me 2. Now let's examine points after it, such as 2. And this is going to give me negative 2 by 2 plus 3, which is negative 4 plus 3, which is negative 1. So now let's imagine the graph again, or any random graph, and just check the behavior around the max and the min. I see that the slope before max is greater than 0 and goes less than 0, and I see that the slope before minimum is less than 0 to greater than 0. Now let's check the behavior of my function. I have that before it is greater than 0 and after it is less than 0. So that tells me that it's going to look like this. And so I can classify the extrema that I have found at 3 over 2 as a maxima. And that's going to be it for this question. Okay, last up, I think we have a divergence question. So let's just briefly discuss what divergence is. Sorry, I think the question meant to state the curl and the divergence. Okay, so curl and divergence measure things on vector fields, and the divergence necessarily. So the divergence measures flow, and the divergence is the dot product between the gradient and the vector field. And so its notation would be this. And when you expand it out, if your vector is in 3D, then it will be the dot product between these. Now let's examine a couple cases. So when the divergence is over 0, you're going to have the flow outward. And so what that means is on my graph, if I have it in 2D, my vector field will look like if I placed water, if I placed water in this vector field, it would flow outward. And so it's going to look like this. Okay, now if I have a divergence of under 0, then the flow is going to be inward. And so if I had water in the vector field, I can imagine the water is flowing towards the origin. Okay, now lastly I have the third case, which is when the divergence is equal to 0. And that means that I don't necessarily have a flow inward or outward. And it typically indicates that I may have rotational behavior. And so the water wouldn't necessarily flow inward or outward. It would be flowing, indeed, in some direction, but it is not inward or outward. Okay, so let's find the divergence of this vector field. I have f is equal to x, y squared, z squared, x squared, y, z squared, x squared, y squared, z. Okay, so now when I take the dot product with the gradient, that's the dot product that I will be taking. Okay, and so this will lead to this statement. Okay, so the derivative of this with respect to x, the x is to the power of 1, so it'll just cancel out as a 1 and form y squared z squared. The derivative of this with respect to y, the y is to the power of 1, so it'll just cancel out as a 1 too, forming x squared z squared. And then the derivative of this last one with respect to z, the z is to the power of 1, so again it will just cancel and form x squared y squared. So for this vector field, I see that it's neither, it doesn't give me a number as the answer that is greater than or less than 0. And what that means is depending on the values of x, y, and z, you'll have a different flow. And so the vector field won't necessarily look static like this, where you have the same type of behavior everywhere. The behavior of the flow will be dependent on your x, y, and z values, is what that is telling you. Now, next up, let's discuss the curl. The curl is similar, and it's going to be the cross product between the two. Okay, and what it measures is when the curl is less than 0, it measures, the rotation. And so when the curl is less than 0, you'll have clockwise rotation. So let's say the z-axis was coming out to me. Then I would have a vector field that looks like this. Okay. Now let's say I have a curl that is greater than 0, I'll have anti-clockwise rotation. And so what that looks like is in the opposite direction. Okay, now lastly, of course, we have the third case, which is when the curl is equal to 0. So equal to 0 cases, since the curl is describing a certain behavior, equal to 0 means that the vector field is telling you nothing about this certain behavior. There's no information on this certain behavior, which means that it has no rotational property necessarily. And so that means like it's flowing inward. It isn't rotating in any specific direction. As an example. Okay, so again, let's find the curl of our vector field. So we are going to take the cross product between these two, and that is going to be d over dx, d over dy, d over dz cross with f1, f2, and f3. We know what they are because we've been given the vector field, so we're just going to put that in to when we are finding the cross product. So ijk, and then d over dx, d over dy, d over dz, and then put in your f1, f2, f3. So x, y squared, z squared, x, let's space them out a little bit more. Okay. So for our first one, we have xy squared z squared, x squared y z squared, x squared y squared z. Okay, so in I, we will have this minus this. And so it is going to be d over dy x squared y squared z minus d over dz x squared y z squared. Okay, minus in my j component, I will have this minus this. And so I have d over dx of x squared y squared z minus d over dz of x y squared z squared. And then lastly, in my k component, I'll have this minus this. And so that is d over dx x squared y squared z, x squared y z squared minus d over dy x y squared z squared. Okay, and then I'm just going to put that all together. This will lead to, in the I component, the derivative of this with respect to y is 2x squared y z minus the derivative of this with respect to z, which is 2x squared y z. So this is obviously 0, minus, in my j component, the derivative of this with respect to x is going to give me 2x y squared z minus the derivative of this with respect to z, which is going to give me 2x y squared z. So obviously this is going to be 0 again. Oh, and then lastly, in my k component, I will have the derivative of this with respect to x, which is going to give me 2x y z squared minus the derivative of this with respect to y, which is going to give me 2x y z squared. So for all of them, I see that I'm subtracting a from a basically, so this is going to be 0, 0, and 0. And so as my answer, I'll get a 0 vector. And so this is going to be the third case that we mentioned up here, where there isn't any rotational behavior that I can give to the entire vector field. It isn't rotating in any specific direction. And that's going to be it for this question. Okay, next up, I'd like to test whether this vector field is going to be conservative. Whether the vector field is conservative will allow me to do certain things with it when it comes to certain theorems and integration. And so I can determine whether it is conservative in two ways. Sorry, my apologies. Yeah, so the vector field is going to be conservative if the curl of the vector field is 0. The second way to do that, to check whether the field is conservative, is using the method that we have here. And a vector field being conservative means that it is path independent. And so that's going to be really important in other courses like chemistry, for example, where state functions are path independent. So we'll have our conservative and we'll have a curl of 0 if you wrote it as a vector field, and in the theorems that I mentioned. So let's go ahead and find the curl. So we have that f is equal to 15x squared y squared and 10x cubed y, 0, it's only two-dimensional. Okay, and so the curl is going to be d over dx, d over dy, cross with what I have. Okay, and so this is going to give me d over dx, d over dy, f1, f2. Oops. And so that is going to be df2 over dx minus df1 over dy. Okay, so let's put in our f2 and our f1. So that is d 10x cubed y over dx minus d 15x squared y squared over dy. Let's go ahead and find out if that's going to give us a 0. This is going to give us 30x squared y minus the derivative of this with respect to y, which is 30x squared y. And that's going to give me 0. And so obviously my curl is equal to 0, and so it is a conservative vector field. So conservative means it's path independent, and non-conservative means that it is not path independent. The integral will depend on the path that I take. And so, yeah, that's going to be it. Okay, and those are all of the questions that I have for you today. I hope you enjoyed today's Q&A session. If you'd like to be able to, if you'd like to be notified of when we post questions, be sure to hit the subscribe button and the bell right next to it so you can get the push notification of when we do post. If you'd like to be able to post questions of your own, be sure to check out the links in the description to the OneClass channel where we do source our questions. This has been Marlyn from OneClass, and I hope to see you